Another question regarding a homework problem. We have a problem similar to this one. The numbers are different. But we have an automobile moving at 35 meters per second, and we know that the automobile can accelerate at negative 0.5 meters per second squared. Now that's not much acceleration. We apparently have a pretty slick surface here, or a steep downhill or something, but that's a pretty low acceleration. And we're asked how long it's going to take to stop given some sort of an emergency that occurs, and also given that there's a 1 second reaction time. Now, during the 1 second reaction time, naturally, we're going to continue moving at 35 meters per second. Okay, we don't slow down to velocity of 0 until here. So we're going to move 35 meters in that 1 second of reaction time, and then we're going to start our uniform acceleration phase with an acceleration of negative 0.5 meters per second squared. Now the individual who posed the problem said, okay, I know that I know VF, and I know that I know V0, and I know that I know the acceleration. Final velocity is 0, initial velocity is 35 meters per second, acceleration is negative 0.5 meters per second squared. And I know that I'm looking for delta S, so I'm going to use this equation. How do I do the algebra to solve for delta S? Well, at the end of the last lecture we did that, and we saw that the strategy is simply going to be first to add a negative V0 squared to both sides, and then to multiply by the reciprocal of the coefficient of delta S, in other words by 1 over 2a. And when we do that, we're going to obtain delta S equals VF squared minus V0 squared over 2a. Then it's a simple matter of plugging in our information and we get our distance. We didn't really need that, incidentally. We could have reasoned it out directly. But before we do that, let's put our information together. Now, the 1225 meters is the displacement during the acceleration phase. To get the total displacement, of course, we're going to have to add that to the 35 meters that we go during the time of reaction. Now that 35 meters is not going to be too significant compared to the 1225 meters, which is the better part of a mile. It's going to take a long time to slow down. Of course, that's a pretty high speed there. If we have a greater acceleration, the reaction time distance will be a little more significant. Now to directly reason this, what do? Well, we go from 35 to 0 at a constant acceleration, then our average is going to be 17.5 meters per second. Accelerating at negative a half meter per second, which is what this means, it's going to take us to change our velocity by 35 meters per second, negative 35 meters per second. It's going to take us 70 seconds, isn't it? So we're going to spend 70 seconds moving at that average velocity of 17.5 meters per second. 70 seconds at 17.5 meters per second is 1225 meters. So again, from 35 to 0 at this is going to take us 70 seconds, half a meter per second every second. It's going to take 70 seconds to get that 35 meters per second. So then the fact that our average velocity is 17.5 meters per second tells us that our displacement is going to be 17 meters per second times 70 seconds, or 1225 meters, consistent with our previous result. It's very important to understand that we need to be able to reason directly when that is possible.